what I haven't shared with you here, but nonmetals will gain an electron, and where metals get smaller, nonmetals get larger when they gain electrons. Okay? And the reason why is pretty easy to realize. Now what you're doing is you're creating more negatives in the same space. And we know that they want to repel. Alright? Now look at nitrogen. Fluorine gains 1, where nitrogen gains 3. So now we're putting 3 like charges in the same area. What's going to happen to the size of nitrogen versus fluorine, do you think, if you compared the two? Which one's going to get bigger compared to its original size? Nitrogen is going to get much bigger. Fluorine's going to get bigger, but it's only adding 1 electron. So think of you're adding 3 electrons. Okay, it's like having a vehicle that's not big enough to fit everybody in, then you're going to have to get a bigger vehicle. Your family size, you got a subcompact, start having kids, subcompact doesn't work anymore. You got to go something bigger. Okay? So you add more and more electrons, the atoms gets bigger. If you take away that, it loses a whole level. Here, they repel. We're not adding protons. If we added more protons, that'd be different. We're not adding protons. Okay? Harder to keep track of the electrons. They get further apart. The atoms get larger. So, any questions on that? So that's what tends to happen when things form ions. Nonmetals tend to form anions. Metals tend to form cations because, and when we look at the configuration, guess what these configurations are over here? They're S2P6. These configurations are S2P6. These configurations are S2P6. They're all octets. Now, there's one that doesn't gain or lose, and guess what that one is? That one's neon, for example, would be 1, because it's already S2P6. So guess what? There's nothing for it to take an advantage of because it already has the octet. The other things are trying to get there. Okay, questions? Does that make sense?
So the octet,
go ahead.
The octet is like the noble gases then?
Right. If you would draw electron configuration for all the noble gases, they would all have S2P6.
Okay.
Yep. The other ones don't. The other ones want to get there. So metals either going to lose or gain. Now, there's some terms we're going to talk about losing and gaining, and there's some values associated with every single element in this process. Okay? Here's the first one. All right? Now, just copy the top for now. We're going to talk about this thing called ionization energy. What is it? Well, it's a term that says, if I look at an atom, and I'm looking to get rid of an electron in that atom, how much energy am I going to have to supply to take that electron away? It's going to be called ionization energy. So, ionization energy is energy required to take an electron away from an atom. We're going to take an electron away. Now, you could take more than one electron away from the same atom. So they have this term called first ionization energy. What is that? Well, you're taking out the first electron from that atom. Okay. And then they've got this other term, it's called second ionization energy. That's what these quotes are for, guys. These quotes down here. Right down on the second. Because everything's quoted exactly the same except the first part and the last part. so that you don't have to write it the same thing out a second time. So, what is the first ionization energy? A, to take out the first electron. Because if it has multiple electrons that'll need to be taken out, they'll be called first, second, third, fourth, fifth, and so on and so forth, depending upon how far you go. So let me preface this with, remember Coulomb's law, and that should help you kind of understand maybe the trend a little bit. Okay, look, Coulomb, all of these are going to be saying Coulomb's law, or that fundamental idea of particles. So, any questions about ionization? So, here's the deal. The smaller the number, the more willing the atom is to give up an electron. If it has a small relative number, these are all relative numbers, because when you look at a number, you're like, I don't know what 300 kilojoules per mole means. But if I compare it to something that says 600 kilojoules per mole, then I know the one that says 600 is double the energy required to remove its electron, right? Right. A mole is a certain number of electrons. It's a big number. So all you have to worry about is the kilojoule. So, hey, if it's bigger, it's harder to take out, the electron. If it's smaller, it's easier to take out. Questions on that? All right? The next one is the opposite. It's the willingness of an atom to say and accept an electron. And it's the analogy I guys use with Christmas. And as a little kid getting something really neat for Christmas, and the excitement level just goes up. Then as you get older and you get like your mom gets a gift from you, and it's like a frying pan. You're like, I'm going to get Mom a frying pan. She needs a frying pan, I think. Okay, and then she gets it, and she's like, oh, thank you. You know, I only have, 10 of these, but thanks, Or like getting her a vacuum. Wouldn't that be good? Get your mom a vacuum.
That's what my mom wanted for Christmas last year.
That's what she wanted. Well, good. But usually if you're, like if I get my wife a vacuum, that would not be good, would it?
Especially on Valentine's.
Yeah.
She got really mad when we didn't get her one.
You could just tell her, hey, we're thinking about you, we don't want to get you a gift that requires work. So that's kind of the analogy you look at. If you would get, a trip to Hawaii versus a vacuum, the excitement level changes, right? So when we look at electron affinity, it's the opposite of ionization energy. It's an atom saying, with this number, it's saying, I want an electron. And so how do you look at this number? Well, it's a little bit different than ionization energy, because we have a negative value that's associated with this number. And the reason why is because we're looking, and we're doing this right now in AP Chemistry, we're looking at this thing called thermodynamics. We won't get to it in here. But it's kind of like this coffee in here. If I open the lid, what happens to the heat energy of the coffee? It's less. Okay, so it's losing. And that would be a negative number. So if it's losing energy, the more energy, when we're looking at electron affinity, that an atom loses, and that's a good thing. Okay, the higher the negative number, the more likely it is to pull an electron in. Because everything, when something loses, it gets to what we call lower potential energy, and lower potential energy is good. Okay? Remember in the past we talked about chores. Which chores do you tend to do? Well, the ones that require the lowest energy. Okay? And so atoms tend to want to get to a low potential energy. And to do that, if they're able to lose more and more energy, that's good. And they want to do that. So when you look at the chart, they'll have negative numbers. And those negative numbers represent energy given off. And that they're more receptive to gaining electrons. Now, if it's 0, they do not want to have anything with pulling in an electron. If it says 0 electron affinity, guess what? It doesn't want an electron. You'll have to maybe do some drawing out of your electron configurations for certain elements. And it's always good to compare high and low, and why? High and low, draw out the electron, you can even do the abbreviated, and the orbital notation. Why? Why do these tend to have drastically, and they're right by each other? This one is 0, this one's high. Why? So then you draw out that electron configuration and you go, there's something here that maybe I can explain. Questions on electron affinity. Wanting to gain an electron. Every atom has electron affinity. I mean, every thing in a group is going to have a number associated with it. Okay? Now the last one involves when atoms tend to get together and bond. And we haven't done much on bonding, chemical bonding. But we know that if two atoms hook together, that's going to be a chemical bond. And it's going to make our compounds. And next unit we're going to do is we're going to talk about compounds. Ionic and ionic first. So, this term called electronegativity. What does it mean? Okay, this is kind of like Green Bay Packers. They sell shares in their teams. You guys know that?
Yeah.
Okay. My dad had one share. He got a certificate. He's got one share. Had it framed. Okay. Well, imagine the amount of shares in the Green Bay Packers are in the millions that are distributed among the shareholders. Yeah. How much share does he have, and how much importance does his voice have in the everyday workings of the Green Bay Packers?
None.
0, basically. Okay? Now, if I have a 50% share, I have a pretty good, my opinion probably matters quite a bit in day-to-day, week-to-week operations. Okay? So what this says, this number is kind of like a share. The bigger the number, the more of an attractive force or share that atom has relative to another one. Okay? So this basically says, hey, if we've got this atom, it tends to have a great amount of attraction for electrons when paired with another atom. And the bigger the number, the bigger attraction it would have. Okay? The lower the number, the less attraction. So we got these two atoms together. Okay? They're hooked together. One of these atoms is going to have an unequal share most of the time. That means the electrons will be, again, the higher attractive between. Another analogy would be if you have two siblings and you guys are supposed to share a vehicle between the two of you. Does anybody in here share a vehicle between the two of you? Okay? You share? Who do you share with? Okay? Now, who drives?
It just depends who wants to drive.
Okay? Who usually drives most of the time between the two of you? Does it matter?
Honestly,
Is it 50-50?
Yeah.
Okay, so you guys have a pretty equal share of it. Okay? But who else shares a vehicle? Anybody else share a vehicle? Nobody else? With your parents?
Yeah.
So, okay, you guys share a vehicle, okay? How much of a share do you have that vehicle compared to your parents?
Probably 70-30.
What's that?
They probably use it 70%.
Okay, so that's an unequal share. She's only able to use it 30% of the time. That's kind of what we're getting at. If over a period of time I look to see who's using it, the one that uses it the most is like the atom here that has a greater share. It has more of a say in those electrons and where they're at. Okay, does that make sense? So those are the three categories that you guys have columns for. So now that you know a little bit more about those categories and how they work, these are your groups. Okay?